Okay, so let's talk about non-deterministic polynomial time a bit more. So we have P and NP. We have P and NP. We have Turing machines. Okay, so P is the set of decision problems that have polynomial time algorithms. Okay, so that's all the pretty much most, I should say, most of the problems that we discussed in the second part of the course. NP is a set of decision problems that have a polynomial time non-deterministic algorithm. So again, a polynomial algorithm where a non-deterministic computer can solve the problem in polynomial time, and that could just be that's literally SAT, right? The algorithm for a non-deterministic computer for SAT would simply be guess an assignment. That assignment will evaluate to true, output assignment if it is satisfiable. And so many problems. So the reason NP is important is because many problems that we would like to solve are in NP. And every problem has an exponential time algorithm. So a lot of these are Turing problems. Okay, if we like the traveling salesman, for instance, package delivery, UPS would love to be able to solve the routing of its trucks more efficiently, so that it could plan a route that visits all houses in the shortest amount of time possible. That would be huge for UPS, but it's actually an incredibly hard problem. And we know that problem is in NP. And we know we know the problems that are in NP, but that aren't in P don't have any known polynomial time algorithms. So UPS is stuck just doing brute forcing these pathfinding calculations on massive supercomputers to optimize their time and resource usage. Okay, and speaking of that, we know that P is a strict subset of NP, and we know that because any problem that a deterministic Turing machine can solve, a non-deterministic Turing machine can solve that problem in polynomial time using like literally the exact same algorithm, right? Non-determinism just makes the machine way, way, way more powerful. Okay, so definitely we know that P has to be a subset of NP, and we know, um, and so there are problems in NP that are in P, and a big example of that are the various shortest path problems we finished discussing um, just in the second part of the course. Okay, so the big question is, do the problems in NP have efficient algorithms? Okay, and that's another way of saying, does P equal NP? If a problem is an NP, we sort of figure that it doesn't have an efficient algorithm just because no one has shown it yet and people have been working on it for so long. But no one has proven a particular problem doesn't have an efficient algorithm. No one has proven that SAT cannot be solved efficiently. But, I mean, it's been a while. So the assumption these days is that P doesn't equal NP, and there are certain problems that simply don't have efficient algorithms. But, no one has proven that strictly. So problems with no known deterministic polynomial time algorithms include the two problems we discussed in the reductions lecture: independent set, vertex cover. Also set cover, which is very similar to vertex cover, and SAT. Um, these these problems all don't have an efficient solution, but they have a non-efficient solution, right? They could all be solved using brute force, right? If vertex cover, we could still solve vertex cover if we take every possible subset of vertices and then check to see if it's a vertex cover or not, right? So pretty much all the problems in NP have inefficient algorithms. They could all be solved brute force wise, but they can't be solved efficiently in polynomial time. Okay? So, what is common to the above problems? And then the commonality is, of course, as I said, they could all be solved using a non-deterministic computer in polynomial time. And again, it's useful to look back and understand what non-determinism is. Non-determinism is simply the idea that your machine will always make the correct choice. It'll always be lucky. So that if it guesses so that if your algorithm says guess an assignment for this formula, it will just guess the best assignment. How does it work? Who knows? I mean, there's no real explanation I could give you that will agree with your deterministic brain. It's just it's just a catch-22. Our brains are deterministic, and we're talking about something that's non-deterministic. So there's no physical explanation for a non-deterministic Turing machine. The best explanation that we could have is that a non-deterministic Turing machine could effectively travel different possibilities, different timelines, all at once. Okay? And then whatever possibility yields the best outcome, that's sort of the time that all the other timelines sort of collapse, and that's the one we go with. Okay? I know it's like sort of super sci-fi and not like not like a very satisfying explanation, but that is one explanation that you could use if you really need it to meld with your deterministic thought process. So as I said, so with independent and set and vertex cover, the non-deterministic algorithm would simply be to check all possible collection of vertices. With set cover, again, it's pretty much the same thing as vertex cover. You could check all possible collections of sets, and sat, you could build a non-deterministic algorithm that checks all possible Boolean assignments. Okay, so that's great. That's great that we could show that's great that these problems could be solved using a non-deterministic computer. But it would be a little cumbersome if for every problem to determine whether it's in NP or not, we would have to propose an NP, a non-deterministic algorithm, right? And it's pretty hard to check if this non-deterministic algorithm works or not. Right? Because with when we showed algorithms, when we proposed algorithms, when we talked about algorithms previously, we still had to show that they're correct, right? But how do you show the correctness of these non-deterministic algorithms? With these cases, they're simple. These are very simple brute force cases. But then there are much more complex. Problems like integer factorization. Would you check every possible factor at once? Maybe, maybe not. Okay, there are a lot of complex non-deterministic problems, NP problems, that's coming up with a non-deterministic algorithm might be difficult. Okay, so what do we do in those cases? Well, how could we use a deterministic computer to verify that an algorithm is an NP? We simply look for checkability. Okay, what's common in all those algorithms, in all those deterministic, in all these non-deterministic algorithms that we proposed before, was that we did the non-deterministic algorithm, right? The non-deterministic computer just basically did a brute force or a random guess, and then it gave you the answer. Okay? So, it gave you the answer, but there's no real way that you would know that it's an answer or not. Right? How do you differentiate between, for instance, an answer 0 and an answer of no? Right? I mean, this is a computer. This is if you for those of you computer, those comp org students of you. But more importantly, how does the non-deterministic computer know that a particular answer is correct? It could check all possible answers all at once. But at the end of the day, the most important thing that it needs to be able to do is check if the solution is correct. That's the most basic part of any algorithm, being able to confirm correctness. So, if a non-deterministic computer could solve a problem in polynomial time, then a deterministic computer should be able to check that that solution is correct in polynomial time. Right? So the answer, the difference. So the answer is that if there is a problem, if a problem is an NP, it means that there is a non-deterministic algorithm that could solve that problem. But we also know that there should be a way to check that the solution to this problem, there should be a way to check that it is a solution to this problem by a deterministic computer in polynomial time. Okay? So that's how we define NP in terms of deterministic computers. For any yes instance, Ix of x, we need to show that there is a proof / certificate / solution that is of length, that is polynomial to length of Ix, such that the given proof can be efficiently checked to see that Ix is indeed a yes instance. Okay? So we need to be able to show that there is some output by the non-deterministic Turing machine. There is some output that a deterministic Turing machine can check in polynomial time. Okay, that's the most fundamental part of algorithms. You need to be able to output a solution, and the solution needs to be able to be checked. Okay, so we say that a problem is an NP if the solution to that problem can be checked in polynomial time. And the solution to that problem could be in any format we want. Any format we want. So for instance, for a SAT formula, the proof, the certificate here, is simply the truth assignments. It's simply a vector from x1 to xn of zeros and ones. 0, 1, 0, 0, 1. Okay? For an independent set, the certificate, I'm going to use this word a lot. For an independent set, the certificate is simply a set of vectors. V1, V23, V107, ... Okay? So, for a homework problem, the certificate is simply your solution. Okay? So, we define an algorithm, CI, as a certifier for a problem X if the following two conditions hold. If for every S in X, if for every instance of X, there is some string T such that the instance in that string T yields a yes, and for every instance of X, then for every instance not an X, then the certifier has to output a no for every T. Okay? So the string S is the problem instance, and T is the solution. It's the certificate. Okay? So we need to have a program that basically could take in a problem instance and a problem solution to that instance and output that yes, this is a solution to this problem instance. Or no, this is not a solution to this problem instance, in which case this is a no instance. S is a no instance. Okay? So there needs to be some polynomial time certifier that could differentiate between yes and no instances of a certain problem in polynomial deterministic time. Okay. So it needs to be an efficient certifier, as I said. And so the problem, let's go through some examples. Okay, so let's say the problem was independent set. Okay, remember, independent simply says given a GV, does it have a independent set of size k, size greater than k? Independent set is simply that no two nodes in the independent set could have an edge between each other. right? That's all that means. So the certifier, so the certificate would simply be the subset of vertices that form the independent set. Okay. And we need to check two things. We need to check if the size of this subset is greater than k. And then we need to check that no two pairs of vertices in S are connected by an edge. Okay. And so how long would this take? This is very easy to do. Just polynomial time. We just take all pairs of vertices in S, and then we check the adjacency list for an edge. Okay? And so we have a polynomial time certifier, and we have a particular certificate, a polynomial size certificate, polynomial time certifier. Therefore, this problem is checkable in polynomial time, and therefore it is in NP. If it's checkable in polynomial time, it means that a non-deterministic Turing machine could take this, really a non-deterministic Turing machine, the algorithm would just simply look like guess a subset, then use this exact equation, use this exact algorithm to check to see if the subset satisfies the problem. If yes, output this. If yes, output this subset. If no, just go to another branch, go to another timeline where you do have an output for this subset. Okay, so same thing for SAT. We have a SAT formula. Does this formula have a satisfying truth assignment? And the certificate is simply an array of 0. Array that denotes the assignments for 0, x of 1 to x of n, and then the assignments for those. Okay? And the certifier simply, what does it do? Certifier simply enters in the assignments, the Boolean, the variable assignments, and evaluates if the expression evaluates to true or not, right? So how long will this take? Well, it takes linear time with respect to the size of the input expression, to this linear time with respect to the size of the SAT formula, right? So it takes linear time, which is polynomial, and we check if every clause under A is satisfied, and yet return yes if all clauses are true. Therefore, this problem, SAT, is checkable in polynomial time. And therefore, since it's checkable in polynomial time, then it means that there exists a non-deterministic time algorithm that will solve it. Again, just guessing all assignments and then checking to see if that assignment is a yes. And so, therefore, this SAT belongs in NP. Okay? So, we went through this already. I think I've beaten this dead horse. And just to note that we are talking about polynomial time reductions here. Okay? Polynomial time reductions. We say an algorithm is efficient if it runs in polynomial time. And to find efficient algorithms, we are only interested in polynomial time reductions. And reductions that take longer, like exponential time, aren't very useful. Why aren't they useful? Because remember our reduction. Let's say x, and then we have, instead of p, we have exp here. Expy. Okay? So remember that our reduction said that if y had an algorithm that ran in something, let's say y runs in O of n to the 4th time. Okay? And let's say this exponential reduction goes to the 2 of n time. Okay? So what does x run as? X, the algorithm for x, it runs in O of 2 to the n to the 4 time. Okay? Not great. Okay? So if ax runs in exponential, if the reduction takes exponential time, then doesn't matter y is polynomial. This whole thing, x would still be in NP, right? Because this simply shows that x is in NP. Now, admittedly, there might be an algorithm for x that is polynomial time. That's fine. Remember, polynomial is still in NP. But this reduction doesn't show that x is in polynomial time. It shows that x is in exponential time, assuming y is in polynomial time. Now, if y was exponential, let's say y is now in 2 to the n, then things get really complicated because now x is 2 to the 2 to the n, which is super exponential. Okay, it's still exponential time, but it doesn't really. But at the end of the day, the major point here is that exponential reduction doesn't really do anything. So an example of an exponential reduction is if we reduce DNF, or if we reduce CNF, a CNF formula, to a DNF formula. Reducing CNF to DNF is exponential, okay? And I won't go into the exact reduction here, but just know that if you reduce CNF into a DNF formula, then the number of clauses could increase exponentially. Okay, so that's why the reduction is exponential. So that's why DNF isn't necessarily in NP. In fact, we know it's in P. Okay, and CNF is still in NP. But that's essentially why exponential time reductions aren't really useful. The only really useful reductions are polynomial time reductions. Okay, so the reduction can't simply be, for an instance of, for an instance of SAT, you just reduce it to every possible. You just do all possible combinations. For every instance of SAT, you just assign all possible combinations, then put it through the certifier, make AY the certifier, and get a yes or a no. That can't be the reduction because trying all possible assignments is exponential. Okay, and then you would have this situation here. So all this is a way to simply say that that we are only concerned with polynomial time reductions, i.e. these types of reductions, i.e. CARP reductions. Okay, polynomial times reductions from one problem to the other. Okay, and if we only use polynomial time reductions, then that'll still allow us to prove A, that if y is polynomial time, then x is polynomial time, or if x is non-deterministic polynomial, then y would also be non-deterministic polynomial. Y would be something greater than non-deterministic polynomial. Okay. So this reduction, actually, we'll discuss that more in a minute. That point more. Okay. So yeah, that's what. So we call polynomial time reductions CARP reductions, and yeah. So one last thing to really beat this dead horse. So let's say we have two decision problems, and x can be solved in polynomial time, and we have a polynomial time reduction from x to y. Then, which of the following is true? Let's say, can y be solved in polynomial time? Maybe y could be solved in polynomial time, but remember our reduction. This is our scale of hardness. X is a lower bound, y is the upper bound. So just because y could be solved in polynomial time, let's say the boundary for let's say the boundary for NP, so for NP is here. Just because y could be solved, so if x could be solved in polynomial time, could y be solved in polynomial time? Maybe. But we also know that any polynomial time algorithm could be reduced to a much harder algorithm, right? So y could be NP, okay? Or y could even be undecidable, as we'll discuss later on. So just because x is polynomial time doesn't mean y is polynomial time. X is the lower bound. Okay? So this is untrue. This is untrue. It can't be this. What about y cannot be solved in polynomial time? Is that true? No. No, 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 no. No, this is not true. This is you could reduce any polynomial time problem to something slightly more difficult. For instance, you could solve shortest paths. For instance, shortest path with all positive weights can be reduced to shortest paths with positive and negative weights. Right? In polynomial time, we have Dijkstra's for this, which takes O of n log n. And we have Bellman-Ford for this, which takes O of nm. Right? So this reduction still works. So y could be polynomial time. Right? So this isn't true. And if y is hard, then x is also hard. Again, that's not necessarily true, right? That's not true because you could always reduce an easy problem to a hard problem, like here. You could always make a problem that's hard, right? Even if let's say we start stuck with shortest path here. Then I could simply do a reduction which adds also solve some SAT formula. Okay, so I just transformed this problem into a NP problem. So I could always reduce a problem that's easy into a problem that's hard, right? I could always do that. So just because this problem is hard doesn't mean this problem has to be hard. Okay, so this is also false. So I mean, it definitely wasn't going to be all of above, so it has to be none of the above for the reasons we discussed. Okay, so that's just a short theory look at reductions, and yeah, we'll move on to some examples of proving NP and NP hardness next. Thanks.